When we use services that use AI behind the scenes, we need to be aware that those can return hallucinations or bad results. And if we plan to use those in production systems, we need to start using some specific architectural patterns that help prevent these kind of issues to reach our users. This is what we'll talk about today, about one such pattern that I discovered. Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from an undisclosed location, not from the Mozaic Works studios as usual. And what I have for you today is an introduction and a review of the architectural pattern that I found that has been created for a completely different reason, but may very well fit into the age of using large language models as parts of our systems. And I find it very useful, which is why I thought about doing a review. So let's get going. So, cloud architecture, the scheduler agent supervisor pattern. This is a post from Clement Vasters, from his blog post, vasters.com. I cannot find the date. Let's see if we can find the date. Yeah, September 27, 2010. So this is a pretty old pattern, but you know, if you've watched me for some time, you know that I love older patterns because I believe that these are the patterns that are actually have stood the test of time, and so these are the patterns that we can use with more confidence. Let's see what this is about, because of course we need to evaluate it as it is and not only based on its age. Maybe nobody used it, so maybe it's not very useful. Even if we don't end up using this pattern, my feeling is that something similar will be needed. Cloud architecture, the scheduler agent supervisor pattern. As our team was starting to transform our parts of the Azure Services platform from a CTP Labs service, I had to look what CTP is. Capable to promise systems. Enable enterprises to commit to customer order based on production resource capacity and inventory. So basically matches, very simplified. These are systems that match the availability in an inventory with the orders. Probably much more complex than that because it's about logistics and this tends to be very complex, but it's for our goals for this article, that's probably enough. So we are looking to transform parts of our Azure service platform from a CTP Lab service exploring features into a full-on commercial service. It started to dawn on us that we had set ourselves up for writing a bunch of enterprise apps. The shiny parts of service bus and access control that we parade around are all about user-facing features, but if I look back at the work we had to go from a toy service to a commercial offering, I'd guess that 80-90% of the effort went into aspects like infrastructure deployment, upgradability, billing, provisioning, throttling, quota, security hardening, and service optimization. The lesson there was when you're boarding the train to shipping a V1, you don't load new features on that train, you rather throw some off. The most interesting challenge for this infrastructure app sitting on the back end was that we didn't have much solid ground to stand on. Remember, these were very early days, so we couldn't use SQL Azure since the folks over in SQL were on a pretty heroic schedule themselves. We also couldn't use any of the capabilities of our own biz because building infrastructure for your features on your feature would just be plain dumb. And while we could use capabilities of the Windows Azure platform while building on, a lot of those parts still had rough edges, as those folks were going through a lot of the same we went through. In those days, the table store would be very moody, the queue store would sometimes swallow duplicate messages, the Azure Fabric controller would occasionally go around and kill things, or normal bugs. So under those circumstances, we had to figure out the architecture for some subsystems where we needed to do a set of coordinated action across a distributed set of resources, a distributed transaction or saga of sorts. This is one thing I wanted to say. When I look at this pattern, it looks very similar with the saga pattern, but there are some interesting differences, and we'll discuss those. But the important thing here is the context, and the context is one in which parts of the systems might not work as expected, and parts of the system might return erroneous data. These are the two important things. Okay. The architecture had a few simple goals. When we get an activation request, we must not fumble the request under any circumstance. We must run the job to completion for all resources, and at the same time we need to minimize any potential for required operator intervention. If something goes wrong, the system better know how to deal with it. At best, self-heal. The solution to that puzzle is a pattern I call scheduler agent supervisor pattern, or short supervisor pattern. We keep finding applications for this pattern in different places, so I think it's worth writing about it in generic terms, even without going into the details of our system. So to summarize, you have a system where parts of it might return erroneous data or might fail. How do you deal with that? And this fits incredibly well with AI, with large language models enabled services. So if you have services that call a language model, you know that that might return what's called a hallucination, and you might need to verify, or they might get stuck, or the content they return might be weird. So, or incorrect, or containing unwanted things. So this situation fits perfectly, but not only that, if you have any kind of systems where parts of it may fail, it sounds like this is an interesting solution. Now, I'm curious how this compares with the Saga pattern, and I'm curious how this compares with circuit breakers, because these are the other two technologies that you can use, the other two patterns you can use in such situations. So let's see the pattern description. The pattern foots on two seemingly odd and very related assumptions. The system is perfect and all error conditions are transient. As a consequence, the architecture has some character traits of a toddler. It's generally happily optimistic and gets very grumpy very quickly when things go wrong, to the point that it will simply drop everything and run away screaming. It's very precisely like that, in fact. I like this description. So, lesson for you, for every software architect. If you want to write a new pattern for people to use, try writing a story like that. The first picture here shows all key pieces except the supervisor that I will introduce later. At the core, we have the scheduler that manages a simple state machine made up of jobs, and those jobs have steps. The steps may have a notion of interdependency or may be completely parallelizable. There is a job store that holds jobs and steps, and there are agents that execute operations on some resource. Each agent is usually front-end by a queue, and the scheduler has a queue or service endpoint through which it receives reply messages from the agents. So the scheduler has some jobs stored in a job store. It passes to agents in queues, and the agents reply through a queue to the scheduler. Okay, that makes sense. So everything is very asynchronous. Steps are recorded in a durable storage table of some sort that has a list of following field: current state, say disabled or active, desired state, say disabled or active, locked until, datetime value, and actor plus any specific information you want to store and eventually submit with a job to the step agent. When things go right, the initial flow is as follows. 1. Submit a new job into the scheduler and wait. 2. The scheduler creates a new job and steps with an initial current state disabled in the job store. 2b, the scheduler sets desired state on the job and of all schedulable steps to the target state and sets the lock until timeout of the step to a value in the near future, for example in 2 minutes. 1b, job submission request unblocks and returns. So this looks a bit transactional in nature. Submit a job into the scheduler and that thing and that is locked, but then it gets unlocked once. Okay, I see, I understand. If all went well, we now have a job record, and here in this example, 2 step records in our store, they have a current state of disabled and a desired state of active. If things didn't go well with having complete or partially washed records or nothing in the job store at all. The client will also know about it since we held on the reply until we have everything done, so the client is encouraged to retry. If we have nothing in the store and the client doesn't retry, well, then the job probably wasn't all that important after all. But if we have at least a job record, we can make it all right later. We're optimists though, let's assume it all worked best. Went well, sorry. For the next steps, we assume that there's a notion of dependencies between the steps and second step depend on the first. If that were not the case, the 2 actions would just be happening in parallel. So you can go to step 3, place a step message and through the queue for the actor for the first step. Okay. Step 4, after the agent has done the work, it places a completion record into the reply queue of the scheduler. 5, the scheduler records the step as complete by setting the current state for disabled to active. 6, the scheduler sets the next step's desired state to the target state and sets the locked until timeout of the step to value in the near future. Right, about when the operation is expected to be complete. Yeah, so it's a bit of a lock system. It's very interesting. It's smart scheduling. I mean, it tries to lock things just to be sure that you don't pull on them, because the other option would be to keep asking them, are you all right, are you all right, are you all right, and that would just make things worse if it's not all right. But if you have a kind of a timeout, then you can verify the timeout and say, oh, it didn't work well, let's see what we are doing. And the time, of course, there's a bit of latency there, so I'm curious what happens if the job is still running after the timeout. What do you do with it? Okay. Once the last step's current state is equal to the current state, the job's current state gets set to the desired state and we're done. So that was the 99% of the time happy path. Yeah, that sounds good. When things go wrong, this is the interesting part. Remember, the principal or errors are transient. What we do in the error case anywhere is to log the error condition and then promptly drop everything and simply hope that time a change in system conditions, human or divine intervention, or at worst a patch will kill matters. That's what the second principle, the system is perfect, is about. The system obviously isn't really perfect, but if we construct it in a way that we can either wait for it to return from a waste state into a functional state, or where we enable someone to go in and apply a fix or a blocking bug while preserving the system state, we can consider a system perfect in the sense that pretty much any conceivable job that's already in the system can be driven to completion. In the second picture, we have agent 2 blowing up as it is processing the step it got handed. Yeah. Now, there's a diagram showing agent 2 doesn't answer. If the agent just can't get its work done since some external dependency isn't available, maybe a database can be reached or a server is talking to spools out server two busy errors, it may be able to back off for a moment and retry. However, it must not retry past the locked until ultimatum that's in the step record. Okay, so that locked until actually means, based on what I'm reading until now, that the service will be, or the job will be killed at the lock until time. When things fail and the agent is still breathing, it may, as a matter of courtesy, notify the scheduler of the fact and report that the step was completely with no result. That is, the desired state and the achieved state don't match. Then notification may also include diagnostic information. Once the locked until ultimatum has passed, the agent no longer owns the job and must drop it. It must even not report failure state back to the scheduler past that point. Okay, so it basically cuts the communication, drops everything, runs away, as you was saying before. This is a very interesting pattern. I like it because it's clean. It's either running or not running, right? And that's very clean. You don't know. Now, the question is, what happens if the agent started to make some changes in the database but didn't get far enough? There has to be some transactional capability in the agent, which means that the dropping is similar with the Saga pattern, the undo step from the Saga pattern. If the agent kills over and dies that it is processing the step or right before or right after, it is obviously no longer in a position to let the scheduler know about its fate. Thus, there won't be any message flowing back to the scheduler and the job is stalled. But we expect that. In fact, we are okay with any failure anywhere in the system. We could lose or fumble a queue message, we could get duplicate message, we could have the scheduler die a fiery death with just being recycled for patching at some unfortunate moment. All of those conditions are fine since we brought the doctor on board with us, the supervisor. Ah, I see now. So you have a supervisor who does some extra things. Cool. The supervisor is a schedule-driven process or thread, of which one of a few instances may run occasionally. The frequency depends on the average duration of operation and the expected overall latency for completion of jobs. The supervisor's job is to recover steps or jobs that have failed, and we are assuming that failures are due to some transient condition. So if the system would expect a transient resource failure condition that prevented the job from completing just a second ago to be healed 2 seconds later, it depends on the kind of system and resource whether it be a good strategy. What's described here is a pattern, not a solution, so it depends on the concrete scenario to get the timing right for when to try operations again once they fail. Okay, so retrying I understand. I don't understand dropping. I'm curious how it deals with that. This desired backup time manifests in the lock until value. When a step gets scheduled, the scheduler needs to state how long it is willing to wait for the step to complete. This includes a backup time padding. Okay. Once that ultimatum has passed, I like how he calls it ultimatum. I wish he would call the locked until value ultimatum. I think that makes sense. Once the ultimatum has passed and the step is still in an inconsistent state, desired state doesn't equal the current state, the supervisor can pick it up at any time and schedule it. Okay, so dropping. Supervisor creates the job store for any inconsistent steps. For those ultimatum has expired, the supervisor schedules the step again. Once the step succeeds, the step is reported as complete. If it fails, we simply drop it again. For failures that allow reporting an error, it may make sense to introduce an error counter round trips to the step, so that the system could detect poisonous steps that fail forever and have the supervisor ignore those after some threshold. Okay, another issue I see with this is the possibility of a deadlock. when jobs are waiting for one another to complete, and then if you drop one job, the other job will never finish, and then you start. So you may go into some infinite cycles there if you are not careful. But that's, I mean, it's possible for the scheduler to detect such a thing. It's really a matter of implementation of the job. Okay, and now the recovery. The supervisor can pursue a range of strategies for recovery. You can just take a look at individual steps and recover them by rescheduling them. Assuming the steps are implemented as idempotent operations. Okay, this is a very important condition. Very important condition. If it were a bit cleverer, you may consider error information that the cooperative and breathing agent has submitted back to the scheduler, and even go as far as to fire an alert to an operator if the error condition were to require intervention, and then take the step out of the loop by marking it and setting the locked until value to some longer timeout. Okay. The job scope, the supervisor may want to perform recovery such that it first schedules all previously executed steps to revert back to the initial state by performing compensation work, or resources that got set to active are getting disabled, again here in our example, and then scheduling another attempt at getting to the desired state. In the step to be above, we'll be logging current and desired state of the job scope, and with that we can also always finding consistent jobs where all steps are consistent and wouldn't show up in the step level recovery query. Oh yeah, so I skipped this part, which is very important. Let me go back. Compensation work. Yeah. All previously executed steps to revert back to the initial step by performing compensation work. Yes, so that's interesting, but who does that? Because if the compensation is done by an agent and the agent cannot do it, then okay, then it's repeated failures. You need an operator to intervene. I mean, it makes sense. You cannot solve everything. Okay. In the step to be, we've been logging, okay, the situation can occur if the scheduler were to crash between logging one step as complete and scheduling the next step. If we're finding consistent jobs with all consistent steps, we just need to reschedule the next step in the dependency sequence, whose desired step is a match in the desired state of the overall job. Okay. So this is very interesting. Let me just clarify this for a minute and then go to his conclusion, where he talks about things that could go wrong. But basically what you have is a job, a set of jobs, that each job has a set of steps. Now a job could be similar with a flow from a Saga pattern. And you pass each step to an agent. The agents are executing those. If every agent is executing correctly, perfect, move on. If an agent is not executing correctly, then the supervisor does two things. First, searches for all jobs. So wakes up occasionally, searches for all the jobs that have not been correctly executed, and perform some actions. It does some compensatory measures, and it restarts the steps based on the amount of failure in the steps and the error messages and so on. You can go and do some things that are more complex, and those are treated separately. Like maybe you need to to send a notification to an operator and set the ultimatum value to today plus 2 days because the operator might need to come in and fix this, do a patch or something. And this allows you to stop any agent securely. Now, there's still one issue here that I have with going back, so the compensatory measures. In a Saga pattern, those are implemented at the level of a service. In this pattern, they seem to be in the supervisor, which is not great. I mean, it could be a problem with duplicated code. And what would be the God object pattern? The God object, sorry, not pattern. The God object coding issue, design smell. That's what I wanted to say. God object design smell. So, okay. Maybe, I'm sure there are situations when that's not the case, and there are situations where this can be a concern. Let me think about comparison with circuit breakers now. So, in a circuit breaker, you have a system that would call, a caller would call, let's say, a microservice. If the microservice doesn't answer, you cut the circuit. Well, you first go into a temporary state where you try, let's say, 1 in 10 requests to actually send to the microservice, and you break the circuit if the microservice is not answering. This is similar but not the same, and I find this a bit cleaner in the sense that you can solve the same issue with this pattern just through the ultimatum value. I find that very interesting. And now what I'm thinking about is, what if you could use the supervisor to also validate responses? So imagine right now about the case that we are discussing in the beginning. You have a large language model, you have a service that uses the large language model. You send a prompt, you get a result. You need to validate the result. You can either have another step in the job to validate the result, which I would prefer, or you could have the supervisor validating the result. The supervisor is particularly useful if the large language model gives a timeout, if it takes too long. Sometimes it happens, right, for some prompts. But other than that, it's not the only way to solve the problem, obviously, but it is quite a clean way to solve this problem. So I like it. I'd like to try it. Let's see his conclusion and then get some conclusions of our own. To be thorough, we could now take a look at all the places where things can go wrong in the system. I expect the survey to yield that as long as we can usually, I expect the survey to yield that as long we can successfully get past step 2b from the first diagram, the supervisor is always in a position to either detect that the job isn't making progress and help with recovery, or at least call for help. The system always knows what its current intent is, which state transition it wants to drive, and never forgets about that intent is logged in the job store at all times, and all progress against the intent is logged as well. The submission request depends on the outcome of 2AB to guard against failures while putting the job any step into the system so that the client can take corrective action. In fact, once the job record is marked as inconsistent, the scheduler could already report success back to the submitting party even before the first step is scheduled, because the supervisor will pick up that inconsistency eventually. Right. So, a few conclusions. I think this pattern is very clean. It is very clean because it has very clear intent, as he was saying. That's what I'm liking. The job is either running, done, or cancelled. These are the three possible states. Nothing else matters. Okay. Where I see a few problems is architecting these agents. So splitting the jobs, splitting into jobs and then splitting the jobs into steps, and trying to make the steps idempotent. Or somehow have the compensatory mechanism. Anyway, this is a very interesting pattern, and I think this has a place in microservices architectures, particularly when you have this kind of architecture, this kind of, so where it most naturally fits workflows. Workflows are especially complicated to implement in microservices. You have the Saga pattern, which is great, but if you have other types of workflows? I've always felt that those cannot be easily implemented with the microservices architecture. It's a bit of a pain. And my feeling is that using this pattern, you can actually do a lot of stuff easier. But it really matters what jobs you have, so how you split the workflows into jobs and into steps. Which makes it a really good candidate for an architectural kata, if I think of it. I'm curious to try it. I'll probably schedule an architectural kata, a performed architectural kata in the autumn for you, if you want to join and test with me this and evaluate with me the application of this pattern. If you have any ideas for the problem that I could choose, let me know in the comments. I'd love to hear from you. So what do you think about this pattern? Do you feel it fits somewhere in your architecture? Do you feel it would help your architecture somehow? What other challenges do you see with it? Let me know in the comments. We love comments, and we love that we received some lovely comments for the last video that really made my day. So, but honestly, even criticism is very useful if it's applied, if it's something that I can change. I'm very interested in hearing about it. Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.